Good evening and welcome back. Tonight we're going to be discussing key attributes for exponential functions. Okay, key attributes for exponential functions. And I have a generalized exponential function here. And exponential functions are going to be where your x value is in an exponent. Okay, so that's f of x equals a times b to the power of x. Okay, and so these a and b's are really going to be the attributes that we're looking at, and there's one more. There's going to be three total. Okay. But first, let's talk about the a and b. Now, the a value is going to be your starting point. Okay, that's going to be your y-intercept. Okay, where this graph is going to touch the y-axis. So, if I give you an example where we have, let's say, a bank account. I'm going to go out and open a bank account. I'm going to put $200 in there to begin with. Okay? And let's say it's going to grow at a rate of 4%. Well, for that example, the 200 would be the A. That would be my starting value. That's where it's going to touch the y-axis. Okay? And then this B here is called a factor. Okay? B is the factor. And that'll tell you whether it's going to be growth or decay. Okay? And for growth, you're looking for B to be greater than or equal to 1. Okay? And then for decay, you're looking for a b value that is less than 1. Okay? So b is the factor. All right? But really, when we talk about the b value, b breaks down into two different things, because look here, it says growth or decay. Okay? Growth or decay. But it's just a factor. So we want to know really what that is. So we're going to look at growth first. We're going to look at the two different ways what b can be. And the first one is growth. Okay? And so for growth, you're going to get a rate on each of these things, all of them. And the rate is going to determine whether how fast this exponential either goes up or comes down towards the asymptote. And so what we're looking at is for b value, b is always going to be a 1 plus or minus and then some r, some rate. Okay? And so for that previous example where we're starting a bank account and we have $200 and we get 4% growth. Okay, the 4% is my rate. All right, so if you're looking at growth, okay, you're looking at a b value that's going to be 1 plus and then the rate. Okay, and then the other one was decay. Okay, you can also get decay functions. Okay, and decay would be maybe tracking the lost value on a car over time. Okay, and that's going to be the 1 minus a rate. Okay, 1 minus a rate. So really, you're looking at two different kinds of functions here. You're looking at something that could be a starting value times, and then for growth, it's going to be 1 plus r to the x. And if we're talking about decay, you're going to get f of x equals some starting value. There will always be a starting value, even if it's 1. Okay? And then for decay, you're going to get 1 minus r. Okay? To the power of x. But really, the only thing that's different in these two things is going to be this here, the plus or minus. That's the only difference. Okay? The only difference. And what that comes down to is basically saying, if we go back to our very first example, okay, where we're starting a savings account maybe. With $200, and it grows or gets interest at a rate of 4%. Okay, well, we know that it's exponential, so you're going to get f of x equals a times b to the x. Okay, and my a value, remember, is the starting value. So what are we starting with here? What are we starting with? We're starting with $200. So if I was going to write that function, then I'm going to start by writing a function that starts with $200. So f of x equals, and then we know our starting point, the a value, is 200. Now we need to figure out what this b is. What is the b value? So now I need to look at this guy. And we know that b is going to be either growth or decay. Now, when you're talking about savings accounts, what that means is that you're getting money. So if you're increasing something, that's going to be growth. Okay, I'm getting more money. Okay, and so I need an R. There has to be a rate. And it gives you it right here. The rate is 4%. Okay, so I know I have 1 minus R for B. Okay, 1 plus R for B for growth. Okay, and so now we just need to put it into the function. But I can't put just 4 there for R, okay, because 4 is a percentage. I want to convert that into a decimal. Okay. So what's actually going to go in there, and since we have growth, okay, we're going to do this in green. What's actually going to go in here is going to be 1 plus, and then 4% as a decimal point is just 0.04. Okay. And then to the x. That's going to be the function. Okay. So there's the two key attributes, the b value or the rate, okay, the factor or rate. Because you can see here that if we simplify in these parentheses, we simplify this rate, this 1 plus the rate there, you're going to get times and then 1.04x. And so that's going to show you that b is indeed greater than 1, okay? So we get growth. Okay, so there's your b value. We got that by doing 1 plus r, okay, for growth. Now let's talk about an example where you get decay, where we lose money, okay? So if we're losing money, let's say you go out and you buy a car or a boat. The second you pull those things off a parking lot, you lose value on it. It loses value because it's not brand new anymore. And the more miles you put on it, the more value it loses. The older it is, the more value it loses. So we can model this pretty closely with an exponential function. So let's say we buy a boat buy a car. Let's buy a car, a really nice one. Let's say we buy a $20,000 car. Okay, for $20,000. And let's say it loses 6% of its value each year. Okay, so we need to pull out our A and B because we know we're going to have f of x equal to some a b to the x. Well, let's look at A. What is A? A is the starting value, y-intercept. And what do we start with? How much money did we spend on that car day one? We spent $20,000. Okay, so A here, starting value, 20 grand. Cool. So now we need to know B. The first thing I want to ask myself is this growth or decay? Okay. And because we're losing value, this is going to be decay, which is going to mean we're going to get a 1 minus the rate. Okay, and it tells us our rate is right here, 6%. That's how much we're losing. Okay, so we can go ahead and write this function. It's going to be f of x equals starting value, 20,000, times, and then my b value is going to be 1 minus the rate, 6%. But again, we can't use a percentage. Okay, that's not going to give us the right b value. So we're going to use the decimal that represents that percentage, or 0.06. And then to the x. Do not forget the x, because that's what makes it a function. Okay, that was what makes it an exponential function. So now that we have that, we have our function, and we can graph it and map how it works out. So I could tell you when x is years, in this many years, that car will be worth this certain value. Okay? And this is going to be 94%? Yeah. So 0.94. And then you can confirm it's decay because b is less than 1. Okay, this value here, 0.94, is less than 1. Okay, and there you have it. Now, so that's the first two key attributes for this. Now, the last one is going to be the one that should be pretty new to you guys. Okay, that one should be fairly new. And it's going to be called asymptotes. Okay, an asymptote. And be careful, because if you know me, you know I can't spell at all. And so the asymptote, I believe, is S-A-S-Y tote. Nope, only one S. Yeah, should be A-S-T-O-T-E. There we go, asymptote. And an asymptote is a line on a graph that some curve is going to come close to without ever touching. Okay, so it's going to get closer and closer and closer. Some curve is going to get closer and closer and closer to some imaginary line on this graph without touching it. And the way I explain that concept, okay, the way we explain a concept like that is, let's take a look at a glass of water. I know these aren't all the same size, but just imagine that they are. Okay, and we're going to number these 1, 2, 3, 4, 5, 6, 7. Okay, and let's imagine that on day one, the water is full. Okay, it's a full glass of water. But I'm going to drink half of it. Okay, so I'm going to consume half of that water. Okay, so this is what's left. All right, so day two, I come back, and this is how much water I have. And I'm going to consume half of that. So on day three, I have half of what was originally there the previous day. And day four, I'm going to consume half again, half of what's left. Okay, and then day five, we're going to do the same thing. We're going to do half of what's there on day four. And then half of that, and then half of that, Okay, and you can see how at the beginning the amount of water drops rapidly. But towards the end, you almost can't notice that it went down at all because I'm only consuming half of what was there on that day. Okay, so here, day one, I had full glass, and so I consumed half of it. Then on day two, I only had half a glass, so I took 1/4 of the glass, half of that, half of that, half of that, all the way down. So if you think about that, if we project that out by days, is there ever going to be a day where I have no water left? And technically, no, because I'm only consuming half of what's left. I'm never going to consume everything. I'm never going to drink everything in that glass. And so that's what this exponential function is doing. It's approaching a value. It's coming close, so close. But it's not actually going to touch that value. It's not actually going to get to it. Okay, so that's what an asymptote is. It's a line that a curve approaches but never crosses or touches. And you'll see one in every exponential function. Every exponential function has an asymptote. Okay, and it cannot touch it. You cannot touch the asymptote. All right, so let's look at this. Look at this exponential curve as it comes down. We want to know the equation for the asymptote because it is a key feature. So I want to know what is that imaginary line that we can't touch. Okay, and as you see, it's getting closer and closer to what value? Getting closer and closer to the x-axis. So here is my asymptote all the way across. Okay, all the way across. And what you can see is the asymptote is actually on the x-axis. So we need an equation for that line. Okay, we need an equation because you have to be able to say this is the equation for the asymptote. So if I want the equation for a horizontal line, it's just going to be y equals and some number here. Well, what is that y value there? It's going to be 0. Okay, so my asymptote is y equals 0. And in almost all of your real-world equations, the asymptote will be 0. But you may come across a situation where that's not the asymptote. So let's take a look at this example here. Okay. We have another exponential function. Okay. And it's roughly drawn. Please forgive my hastiness. But here's an exponential function. You can see it's decay because it's going down as we move to the right. So that's decay. But it kind of levels off way before we get to 0. Look at this huge gap. So I know my asymptote isn't going to be down here. But what if I put the asymptote on 2? Oh no. Look, we touched the graph, so that can't be the asymptote. So what value am I approaching without not crossing? If I draw a line across here for 1, you can see it gets very, 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 very close, but then it kind of levels off and it looks like a horizontal line. Well, it's not technically horizontal, but it's not crossing the y value of 1. Okay, it's not going to cross this line here. So I know that that is my asymptote. So what's the equation for this blue line? Well, again, a horizontal line is just going to be y equals, and then the y value it touches, so 1. That would be my asymptote in this example. Okay. So now you know about 3 different key attributes. You know about the starting value, okay, the y-intercept, the rate, the factor or rate, and you know about the asymptote. Okay. Thank you very much.